Welcome everyone to this first part of my playlist about the best methods to convert carboxylic acids into acyl chlorides. Acyl chlorides are important electrophilic acylating reagents and are usually more reactive than anhydrides or active esters. Acyl chlorides are the starting material of choice for Friedel-Crafts acylations and the acylation of weak nucleophiles. In this video, we'll have a look at the use of thionyl chloride as deoxychlorinating reagent. This is one of the most common reagents for this reaction, its main advantage being its low boiling point and that all byproducts are gases. With older batches of thionyl chloride or a large excess, however, small amounts of non-volatile catalyst poisoning sulfur derivatives may contaminate the final acyl chloride. If at a later stage catalytic hydrogenation is required, then oxalyl chloride or phosgene may be superior to thionyl chloride. These reagents are discussed in the second video of this playlist. In part 3, I show you some examples of the use of phosphorus chlorides, mostly phosphorus tri and pentachloride. These are more reactive but less selective deoxychlorinating reagents than thionyl or acyl chlorides, and sometimes already react below room temperature. No catalyst is usually required, while with thionyl chloride or phosgene, some catalyst, usually DMF, must be used to enhance the reaction rate. From an economic point of view, phosgene and thionyl chloride are the most inexpensive deoxychlorinating reagents available. Hydrogen chloride cannot usually be used, and I'll show you why in a minute. Other suitable reagents for converting carboxylic acids into acyl chlorides include cyanuric chloride and isolated chloroiminium chlorides, but these are used less frequently and will not be discussed here. Chloroiminium chlorides are usually formed as intermediates from phosgene and thionyl chloride and catalytic amounts of amides or ureas. Deoxychlorination of carboxylic acids with the reagents mentioned above is not always the most affordable route for the large-scale preparation of acyl chlorides. Acetyl chloride, for instance, is mostly prepared from acetic anhydride and hydrogen chloride, as shown here. Just like the formation of ketene by pyrolysis of acetic acid, the reaction of acetic anhydride with hydrogen chloride is reversible and can only succeed if acetyl chloride is separated from the acetic acid before condensation. Acetyl chloride is mostly used for Friedel-Crafts acetylations, for the preparation of mixed anhydrides with other carboxylic acids, and for the acetylation of alcohols or amines. Benzoyl chloride is prepared industrially by hydrolysis of benzoyl trichloride with the precise amount of water. Alternatively, instead of water, benzoic acid may also be used. Thus, geminal di or trichlorides are another type of deoxychlorinating reagent. Benzoyl chloride is an important starting material for the manufacture of benzoyl peroxides, which are used as radical starters and curing agents for polymers. Further uses include Friedel-Crafts benzoylation and the acylation of alcohols or amines. In my playlist about the conversion of aliphatic alcohols into alkyl chlorides, one video was dedicated to the use of hydrogen chloride as deoxychlorinating reagent. Carboxylic acids can also be converted into chlorides by hydrogen chloride, but the equilibrium lies far on the side of the acids, and it is technically difficult to separate the water from the acyl chloride before hydrolysis occurs. This here is an example of the preparation of benzoyl chloride from benzoic acid and hydrogen chloride. The reaction was conducted in the gas phase at 330 degrees Celsius, and large amounts of hydrophobic solvents such as bromobenzene and xylene had to be used to prevent hydrolysis of the product. Hydrogen chloride at 330 degrees Celsius and in the presence of water is extremely corrosive, what, together with the required hydrophobic solvents, probably made this process more expensive than the benzoyl trichloride route. As mentioned above, acetyl chloride is manufactured from acetic anhydride and hydrogen chloride. Reactive esters or mixed anhydrides of other carboxylic acids have also been converted into acyl chlorides by treatment with hydrogen chloride, even in small-scale laboratory preparations. Some examples are shown here. These include propenyl acetate a ketene dimer, and the mixed carbonic carboxylic anhydride of FMOC-phenylalanine. I probably won't make any video about acyl fluorides, bromides or iodides, because these are almost never used in organic synthesis. As shown here, acyl bromides are significantly more reactive than acyl chlorides and should be tested if some weak nucleophile, for instance an unreactive aniline, cannot be acylated with an acyl chloride. Such instances are rare, however. Acyl bromides can be prepared from carboxylic acids and phosphorus tribromide. Thionyl chloride is prepared on a large scale as deoxychlorinating and dehydrating reagent and as cathode for certain types of lithium batteries. One process consists in the gas phase chlorination of mixtures of sulfur dioxide and sulfur chloride, but sulfur trioxide or sulfur dichloride can also be used as starting materials. Thionyl chloride is not very stable and decomposes slowly at reflux temperature into sulfur chloride, chlorine and sulfur dioxide. Because of its low boiling point and price, most deoxychlorinations are conducted with an excess of thionyl chloride without any additional solvent. Alternatively, only a slight excess of thionyl chloride and some acid-resistant solvent can also be used, such as dichloromethane, isopropyl acetate or toluene. The uncatalyzed deoxychlorination of carboxylic acids by thionyl chloride is assumed to proceed as shown here. If the starting acid is weak and electron-rich, the initially formed mixed anhydride will probably decompose by formation of an acylium cation. With stronger acids, however, an intramolecular concerted displacement of oxygen bichloride may occur, as in the SNI reaction of aliphatic alcohols. This path seems to imply a higher activation barrier, though, because strong acids, such as for instance trichloroacetic acid, cannot be converted into acyl chlorides by thionyl chloride without catalyst. One potential side reaction is the formation of anhydrides, especially cyclic anhydrides from dicarboxylic acids. These do also react with thionyl chloride, but more slowly than free acids. Bases such as pyridine or trialkylamines can enhance the rate of anhydride formation even further. Because the outcome of uncatalyzed deoxychlorinations with thionyl chloride depends a lot on the precise structure of the starting acid, the use of some catalyst is often necessary and usually the preferred approach. Deoxychlorinations with thionyl chloride or phosgene are usually catalyzed by DMF. Amides or ureas are converted into chloroiminium chlorides by these reagents, as shown here. Reaction of these salts with carboxylic acids yields acyloxyiminium chlorides, which decompose into the starting amide and the target acyl chloride. So, why do deoxychlorinations proceed faster in the presence of amides than without amides? I couldn't find any precise kinetic measurements, but my best guess is that mainly the two steps shown here should be much faster with amides than without. The upper two reactions on the slide would occur in the catalyst-free version of this reaction, the lower two reactions in the presence of amides. Carboxylic acids are less nucleophilic than amides and should therefore react more slowly with thionyl chloride than amides. Then, chloride is a very weak nucleophile, and the last carbon-chlorine bond forming step could therefore be rate determining. Because chloride is negatively charged, it may react more slowly with the neutral mixed anhydride of the acid with thionyl chloride than with the cationic acyloxyiminium salt. Because of the great relevance of this reaction, a large number of catalysts have been tested. Substoichiometric amounts of amines will be completely neutralized by the hydrogen chloride and sulfur dioxide formed, but these salts still can act as catalysts. As already mentioned, however, bases can promote the formation of anhydrides, which require higher reaction temperature and longer reaction times to be transformed into acyl chlorides. Then, acyl chlorides with alpha hydrogen readily eliminate hydrogen chloride upon treatment with bases. Carboxylic acids can be activated by thionyl chloride in the presence of an excess of pyridine, but the resulting activated intermediate is not always an acyl chloride, but some pyridine derivative. These may, however, still be useful acylating reagents for alcohols or amines. If the aim is an isolated acyl chloride, though, the use of an excess of pyridine or another base is not a good idea. The most common catalysts for this transformation are formamides, or the more stable tetraalkylureas or NMP. Formamides are, however, sterically more accessible and more reactive, and usually the better catalyst. Other catalysts are quaternary ammonium salts and phosphine oxides. For the latter, I'll show you an example later. In some instances, the removal of the catalyst from the product can be an issue. The use of an immobilized catalyst, which can be recovered by filtration, may be a good alternative in such cases. Various polystyrene or silica-bound catalysts have been shown to enhance the rate of deoxychlorinations. So, let's check some specific examples. Because acyl chlorides with alpha hydrogen are strongly CH acidic, acyl chlorides, such as the product of this reaction, do readily racemize. In this case, the scale-up of the reaction only succeeded when the reaction with thionyl chloride was conducted at room temperature. Interestingly, no catalyst was required. Protected alpha-amino acyl chlorides are more resistant to racemization than the previous example, but do sometimes decarbonylate. This was not the case here, and a high yield of acyl chloride was obtained with just a slight excess of thionyl chloride in isopropyl acetate as solvent with 5% of DMF as catalyst. Other catalysts were tested, for instance tertiary amines and dimethylacetamide, but none of them was as effective as DMF. Because thionyl chloride is a Lewis acid and because of the liberated hydrogen chloride and sulfur dioxide, deoxychlorination reaction mixtures become strongly acidic. Terzbutyl carbamates or terzbutyl esters are sometimes cleaved during such reactions, but examples have been reported where such groups remained unchanged. In this example, a Boc-protected amine was not extensively deprotected after 4 hours in refluxing thionyl chloride. Also, acetals are acid-sensitive and may be cleaved during deoxychlorinations. In this example, an acetal was converted into an enol ether. Acids that readily undergo thermal decarboxylation can sometimes be converted into acyl chlorides by treatment with thionyl chloride at low temperature. If this does not work, a more reactive reagent must be chosen, for instance phosphorus pentachloride. In this example, a beta-keto acid was transformed into an acyl chloride already at -4 degrees Celsius, without any catalyst. As shown here, aliphatic amine hydrochlorides do not react with thionyl chloride, and unprotected amino acid hydrochlorides can be directly converted into acyl chlorides. In this example, also the alcohol was completely deoxychlorinated. If the amine is strongly basic, its hydrochloride won't react with the acyl chloride unless the product is heated strongly. Ammonium salts of weaker acids, though, such as acetic acid, will react faster with acyl chlorides than hydrochlorides. You can find a more thorough discussion of the acylation of ammonium salts in my videos about the acylation of amines. Less basic amines do react with thionyl chloride, even in the presence of hydrogen chloride, and can be transformed into sulfinyl amines, as shown here. Despite the large amount of hydrogen chloride formed as byproduct, a substantial yield of sulfinylamine was obtained. Interestingly, these sulfinylamines sometimes hydrolyze faster than acyl chlorides. In this example, the sulfinylamine was hydrolyzed selectively by addition of 2.3 equivalents of water in acetone. Amazingly, the final acyl chloride was precipitated in high yield and purity by addition of a large excess of water. The main byproducts were less than 1% of a mixture of an amide and an anhydride. Acyl chlorides can sometimes be isolated by aqueous workup with a hydrophobic solvent, such as dichloromethane or xylene. I would use brine instead of pure water, in order to keep the organic phase as dry as possible. The pH of the aqueous phase can also be critical for such a workup, and should ideally be around 7 or slightly acidic. Aminobenzoyl chlorides can of course only be isolated if the amino group is sufficiently unreactive, as in the example on this slide, or protected as hydrochloride. When hydroxy acids are converted into acyl chlorides, also the alcohol may undergo deoxychlorination, as in this example, or elimination. If the alcohol is too resistant to nucleophilic displacement, a chlorosulfinate or sulfite may be formed. Interestingly, even salicylic acids can be converted into acid chlorides. Phenols only react with thionyl chloride upon heating, and if the acyl chloride formation is successful at low temperature, then the phenolic hydroxyl group can remain unchanged. Under similar conditions, however, the authors were not able to prepare 3 or 4 hydroxybenzoyl chlorides. These seem to be inherently too unstable and oligomerized to polyesters. Only acid-sensitive carboxylic esters, such as terz-butyl or some benzylic esters, will be cleaved by thionyl chloride. Under forcing conditions, though, even simple methyl or ethyl esters may be cleaved. In this example, phthalate was converted into chloromethylbenzoyl chloride by heating with gaseous thionyl chloride to 165 degrees Celsius. Phthalate is not really a benzylic ester because benzylic CO bond weakening requires this bond to be perpendicular to the plane of the arene. Thus, this reaction probably proceeded by an initial acid-catalyzed cleavage of the ester CO bond. Phthalic anhydride is also quite resistant to deoxychlorination by thionyl chloride. In this optimized procedure, triphenylphosphine oxide was used as catalyst, and again a high reaction temperature was required. Let's now have a look at some further potential side reactions. Thionyl chloride decomposes upon heating into chlorine and sulfur chloride. Therefore, thionyl chloride is also a chlorinating and sulfanylating reagent, and can cause the formation of numerous unexpected byproducts, in particular from electron-rich carboxylic acids. Because deoxychlorinations of acids are best conducted without any base, these reactions will turn strongly acidic as hydrogen chloride and sulfur dioxide are formed. Thus, any transformation that acids can bring about may also occur upon treatment of a carboxylic acid with thionyl chloride. One of the playlists of my channel is about the conversion of alcohols into alkyl chlorides. This can also be accomplished with thionyl chloride, but with unreactive alcohols, sulfites may be obtained as main products. This occurs particularly readily with diols, as shown here. CH-acidic compounds or electron-rich arenes may be sulfinylated at carbon by thionyl chloride, as in this example. Such reactions will be difficult to prevent, but may be suppressed by avoiding a large excess of thionyl chloride. Thionyl chloride is an oxidant and can also chlorinate and thiolate CH-acidic compounds, as in this example. Ketones may even react quite violently with thionyl chloride after an induction period. In this example, malonic acid was chlorinated by thionyl chloride in acetic acid as solvent under surprisingly mild conditions. Because acyl chlorides with alpha hydrogen enolyze quite readily, these may be chlorinated by an excess of thionyl chloride if the reaction temperature is too high, as in the second example on this slide. Cinnamic acids may even be converted into benzothiophene, as shown here. Again, this seems to occur at rather high temperatures only, and may be prevented by conducting the deoxychlorination at a lower temperature. Here, instead of the expected dichloride, dichloromaleic anhydride was obtained upon treatment of acetylene dicarboxylic acid with an excess of thionyl chloride. Even pyridine is oxidized by thionyl chloride. Although this reaction was run for 3 days, small amounts of this pyridine dimer will always be formed if pyridine is used as catalyst and may contaminate the final product. DMF is often used as catalyst for thionyl chloride-mediated deoxychlorinations. It has been found that thionyl chloride can convert DMF into dimethyl carbamoyl chloride, a known human carcinogen. Carbamoyl chlorides are much less reactive than acyl chlorides and remain largely unhydrolyzed and in the organic phase during aqueous workups with toluene or dichloromethane. Thus, this byproduct may find its way into the final product of a synthesis. I'm not quite sure if this carbamoyl chloride is indeed mutagenic, because mutagenicity tests are often run in DMSO as solvent. It is known that DMSO is converted into a mutagen by electrophiles, and this alleged mutagenicity of dimethyl carbamoyl chloride may just be an artifact. Anyway, one should be aware of these issues. Here are some more examples, but many more have been reported. Particularly instructive are the optimized procedures in organic process research and development and in organic synthesis. Part 2 of this playlist is about the use of acyl chlorides and phosgene as deoxychlorinating reagents. These do not contain sulfur and sometimes bring about deoxychlorinations under milder conditions than thionyl chloride. See you then.